So first I'm gonna derive some equations for standing wave on a string, the possible harmonics frequencies of a standing wave. So first let's see. So if you have a string which is fixed at both ends, and you generate the frequency, you provide the signal using a mechanical vibrating. That's how we do in a real lab. You put a mechanical vibrator and it vibrates the string, and you can slowly change the frequency, until you get the standing wave patterns. So starting with what's the fundamental or the first possible harmonic. So first possible, so this is node and node, and the first possible is this pattern, right? This wave, and it will be reflected off the other end, and they form a standing wave. This is called a standing wave, right? The wave will go this way, and the wave will be reflected that way, and they will form, if the boundary condition is met, then they will form a first standing wave. This is called fundamental or first harmonic, right? And the node have is this node has to the this both ends, since both ends are fixed, they have to be the position of node. Node means zero vibration, right? And this is the antinode, so you have only one antinode. An means antinode. So first harmonic has one antinode and two nodes. So what's the first possible frequency? So we're going to find the frequencies, right? First of all, it has to meet this condition. Let's say L is the length of the string, and that has to be equal to, you slowly change the frequency until it matches this condition. So length has to be equal to, so what's the distance between node to node? So node to node distance is half the lambda, right? Because in a full wave like this is lambda over 2, right? Lambda over 2. Same thing from antinode to antinode. Okay, so L has to be lambda over 2, right? And let's call lambda 1 because we're finding the first possible. And lambda 1 is twice L. And so then speed of wave is lambda times frequency. So the first frequency, first harmonic or first possible frequency is this. So V over lambda 1 is twice L. So that's called fundamental or first harmonic. So that's the first harmonic or fundamental frequency in a string like that. So it just depends on the speed of a wave on a given string, which depends on various factors, where V is, remember, a square root of force of how much tension you put divided by the linear mass density, mass per unit length of the string. Okay, so now let's find the next possible harmonics, right? So you again slowly change the frequency. The length of the string is same, right? What you can change is the frequency of the dial, frequency of this mechanical vibrator. You slowly change the frequency. Also check out my animation video. So until you see next pattern. So next pattern possible is, so remember, note that however you change, actually this has to be the position of node, because it's clamped. So next possible has to be like this, right? Next possible standing wave pattern is this. There's no possibility between these two. So there are three nodes, two antinodes. So in terms of wavelength, right, what would be the length in terms of, so it's a full wave, right? Like this, it's a full wave. The length has to match this condition, L2. So L is lambda 2, right? And this can be written as 2, lambda 2 is twice L, right? And then what's the second harmonic frequency? So is speed of wave divided by lambda 2. So right, I'm sorry, this is just L. So V over L, and this can be written as this, V over twice L, right? This can be written as 2 divided by 2 is just 1. And because why? Because this whole thing, V over twice L, remember, is our first harmonic formula. So F2, which is the second harmonic, is just twice the first harmonic, right? second harmonic or second possible frequency of standing wave is just the two times the frequency, two times the first harmonic. There's no possible frequency between that, right? Third, let's do one more diagram, and then you can generalize. So what's the next? So again, you slowly tune the frequency, right, until you see the next pattern. So next pattern, you will have 5, 3, 4 notes. So let's put it here like this. So it must be like this, right? So the next pattern after that is this. This is node, this is node. You have 3 antinode. Third harmonic means 3 antinode. So length has to meet. So this, how much is this wavelength in terms of wavelength? So this is full wave, this is half wave, this is full wave, and this is half wave. So L has to meet 3 half, right? Is 1.5 lambda. So 3 half. This is third harmonic, so lambda 3. So length has to match this boundary condition, 3 lambda 3 over 2, right? And lambda 3 is twice L over 3, right? And then your F3, the third harmonic frequency, is then V over lambda 3. So V over twice L over 3 is 3 V over twice L, right? And again, this whole thing in the bracket is just the fundamental frequency. So it's turned out actually very simple relation. So third harmonic is just 3 times the first harmonic. And now you can generalize. So in general, you can say, right, the standing wave on a string fixed at both ends has this relation. So any number of harmonic, right, is just the n times the first harmonic. That's the general relation. So where n can go from 1 to any whole number integer, right? So that's it. So here are some sample problems on standing wave and superposition. So here's the first example I randomly picked. So here, this is a string fixed at both ends, clamped at both ends, and this is the standing wave pattern at some resonance, at some harmonics. We don't know the number of harmonics, you know. Here's the standing wave pattern you're given, and the length of the string is 2 meters. That's given, fixed at both ends, and the wave speed is 40 meters per second. The speed of wave here in this string is given to you, 40 meters. What is the frequency of the standing wave as shown? So what's the frequency of this wave? So that's what it's asking. So first you have to, now since length is given, so how much is the wavelength? You know, how much is the length of the string in terms of wavelength? So let's count that. So 1, 2, 3, right? This whole length has to be 3 times lambda, because 1, 2, 3 lambda. That should be the position, and you're given the L. So lambda is L over 3. So 2/3, right, meters. And then velocity is given. So frequency is just V over lambda from the wave relation. So V is 40, is 2/3, right? Is then is 60 hertz. So the frequency of this particular harmonic, right, this particular standing wave must be 60 hertz. Now let's do the next one. A bass guitar string is 89 centimeter long with a fundamental frequency of 30 hertz. What is the wave speed on this string? So bass guitar means again a string fixed at both ends, and it says it's vibrating in fundamental mode. This is the fundamental, right? And it's give you the frequency of the fundamental. This is the first harmonic or fundamental, right? And its length is 89 centimeter, and it's asking what's the wave speed, what's the speed of this wave in this on this string, right? And just match the condition. Again, this is node and node. The length has to match lambda over 2, half the wavelength, right? That's what you need to do. So first find the lambda. Lambda is twice L, and 2 times 0.89, right? And that's the wavelength of the given string, and so this is 1.78 meters. So the speed of wave V is lambda times frequency. So lambda is 1.78 and frequency is 30 hertz and 53 meters per second. Okay, so next problem is like this. It has two parts. So what are the three longest wavelengths of a standing wave, on a 240 centimeter long string fixed at both ends? Okay, so you're finding the first three longest wavelengths, right, for a standing wave pattern. So first question is fixed at both ends, right, like this, and you have two nodes. And so we're finding lambda 1, lambda 2, lambda 3, right? So length of the string, this length is 240 centimeter. It says 2.4 meter, right? That's given. And now this is easy, right? So three possible wavelengths, right? So the first one is, so you can draw the wave pattern. Lambda L has to be lambda over 2, right? So lambda 1 is just twice L. So 2 times 2.4, 4.8 meters. What's the next? Just keep drawing. So next is, it will have three nodes, two antinode. So that's the next wave pattern, standing wave pattern. So length has to be, this is a full wave, so lambda 2. So lambda 2 is just L, which is 2.4 meters. So that's second. What's the third one? Length is same. So third one must have four nodes. So first fix the node and then draw the pattern. That will be a lot easier. Okay, so what's the condition? So L has to be, this is one wavelength and half of wavelength. So 1.5 means 3/2 lambda, right? So L has to be 3/2 lambda, that it has to match this condition. So lambda 3 is 2/3 L, right? So 2/3 of L is 2.4. So lambda 3 is 1.6 meters. So these are the three longest wavelengths. So 1.6, 2.4, and 4.8 meters possible harmonics. Now second part. Now second part gets interesting. Now it says, second part says, find the same thing, the three longest wavelengths for a standing wave on a same string, right? I mean same length, 240 centimeter, with one end fixed and other end free to oscillate. So now it says like this. So one end is fixed, right? Still fixed, but other end is free to vibrate. So how do you do that? You put a ring on a pole and then you generate the wave from here, but fixing here, put the mechanical vibrator here, right? And then you oscillate. And it's acting, now this is a ring, is free to vibrate here, it's open end. So if you do that, what will be the three possible wavelengths? So what's the first possible? So this is free to vibrate, right? It's free to vibrate. Then that should be the position of antinode. This should be the position, still position of node. This should be the position of antinode. Why? Because this is free to vibrate, right? So then what's the possible first frequency? So first frequency would be, this has to be node, this has to be antinode. So this is the first possible, standing wave. So then what's the boundary condition? So length has to be equal to, this is node to antinode distance, which is half of lambda by 2, so lambda by 4, right? So not lambda by 2 now, unlike this. One end, this changes the boundary condition, right? So that's important to note. And then so your L has to meet this boundary condition. So lambda 1 is 4L, right? And but length of the string is same, 2.4. So that's your answer. So yeah, so 9.6 meters. So that's your one of the longest wavelength. Okay, now next possible. What's the next possible? So you have same length. One is free to vibrate, remember. So you'll have now two nodes like this. So that's the next, right? Next possible. Two nodes, two antinodes. And so this is antinode, node. So what's the distance from here to here in terms of wavelength? So this is lambda over 2, and this is lambda over 4. So that's how to lambda over 2. It has to satisfy this boundary condition. From here to here, it's lambda over 2 plus lambda over 4. It's 5 lambda over 2, 3 lambda over 4, right? 4, 3 lambda over 4. It's lambda 2. Okay. Now next possible harmonics is L has to satisfy, the lambda has to satisfy this condition. Lambda 2 is 4/3 of lambda. 4/3 of length is 2.4. Okay. 4 divided by 3, 3.2. So the next possible wavelength is 3.2 meters. Okay, one more left, right? One more harmonic, same problem. So next possible harmonic, same length. Now it will have 3 notes. Because this has to be the condition for empty node. That changes everything. Okay, so node, 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 antinode, antinode, antinode. Okay, so now the frequency, the lambda has to satisfy this condition. Now from here to here is lambda, full wave, and this is lambda over 4. So it's lambda plus lambda over 4. So it's 5 lambda over 4, right? So it has to, this is third harmonics. So L has to satisfy 5 over 4 lambda 3. Lambda 3 is 4 over 5 lambda L. So 4 over 5 is 2.4. So that has to be 4 into 2.4 divided by 5, 1.92. 1.92 meters. Okay, these are the possible harmonic wavelengths, frequencies, you know, if one end is free. So here's the next problem. This problem is actually from the actual lab. Actually, that's what we are supposed to do in a lab to see the standing wave. So here you provide the tension by hanging mass on a string. String is fixed at both ends with the pulley here and fixed at the pole, and use the mechanical vibrator. Here's the mechanical vibrator, which you can change the frequency of this mechanical vibrator to see different possible modes. So it says this standing wave is oscillating in M3 mode, that means third harmonic, right, as shown, with a frequency. So its third harmonic frequency is given 180 hertz, right, and a maximum amplitude. So this maximum amplitude is 5 millimeter. The total mass and total length of the strings are this. So mass of the string is 4 gram, so 10⁻3, and length is 1.51 meter, right? These are the given total length and total mass of the string. First question is, what's the wavelength of this wave? And that's really easy. First part is, so this is in third harmonic, right? So third harmonic is M or N. So length has to satisfy 1.5, so 3/2 of lambda, right? Length has to satisfy that, right? So then wavelength has to be 2/3 of L, 2/3 of and this the total length is 151, right? But this length is given. This length, it says, is 1.21 meter, 1.21. So lambda, the wavelength of this wave, standing wave pattern here, is 0.81 meter. So that's the first answer, really easy one. Second question is the speed of wave on a string. What's the speed of wave on a string, right? So first of all, what do you need? Let's see. So speed of wave on a string, you can just do V is lambda f, because frequency is given, lambda we have found. Lambda is 0.81, frequency third harmonic is given 180. So speed of wave, standing wave on a string is given 145 meters per second. Okay, that's the, and part C, what's the tension in the string? So how does it relate with the speed of wave? So remember one formula: speed of wave on a string depends on the force of tension and mass per unit length. So what is Ft is the tension in the string, right? That's you'll have to find out somehow. Mu is mass per unit length of the string, right? As the mass per unit length, m over L. That you can find. So mu is total mass of the string, total length. Total mass is given 4 gram, 10 to the power -3. It must be in kilogram. Length, total length is 1.51. So that you can find out. So if you do the 0.00265 kilogram per meter. Now you need tension force, right? And then you can solve for tension force from here. So you already got that. You already know the speed. So from this, V square is F of T over mu. So tension force is mu V square. Mu is 0.00265, which is the mass per unit length, which is the linear mass density, times V is 145 square. So that's the tension. So if you do that, 55.6 newtons. Okay, so that's how you do. Okay, now last part is, what's the mass of the vibrating portion of the string? Just the vibrating portion. So where is the vibrating portion? So only this portion, right? 121 meters. This is the vibrating portion. So it's asking what's the mass of the vibrating portion. So then you use the linear mass density. Linear mass density will be constant, right? Is the total mass over total length, or mass of the vibrating portion, because since density is constant, length of the vibrating portion. That's all. And you know the length, which is 121 centimeter. So the mass of the vibrating portion is mu times the L vibrating, not the whole length, vibrating. Mu is, which is the density, remains constant, 0.00265, and the length of the vibrating portion is 1.21 meters. So that's your answer. So 3.2 in terms of gram. Okay, that's your answer. Okay, so that's how you solve. Okay, so here's the last problem. So this is a waves on a pipe problem. Okay, waves, standing wave on a pipe. So just like in a string, you can set up a resonance or standing wave in a pipe, organ pipe or any pipe. The lowest, so there are two parts actually. So first part is, what's the lowest frequency in the audible range? The lowest frequency in the audible range is 20. That's the lowest frequency, right? What is the length of the shortest open tube needed to produce this frequency, right? So you're finding the lowest or fundamental frequency, which frequency should be 20 hertz, right? You should be producing a you're making a fundamental frequency as 20 hertz. First part is for open end tube. So first, open means both ends opens like this. So what's the fundamental frequency? What's the length? What's the length of the pipe you need so that you produce 20 hertz as fundamental? So this is free, right? Free means antinode, remember, because air particles then can vibrate freely. So free means antinode, fixed means node position. So then what's the first possible harmonic? So first possible means one node, just one node like this, right? There's no other possibility. This should be the fundamental wave pattern, standing wave. Just one node, two antinode, because it's free to vibrate here. So in terms of wavelength, what would be the wavelength here? Antinode to antinode is lambda over 2. So L over lambda over 2. This has to satisfy this boundary condition, right? So but one more thing here you have to do, you have to convert this frequency to lambda first, and then you can find. So how do you find that? So speed of this is sound, right? We're talking about sound is again v times f is the wave speed. So I'm sorry, lambda times frequency. Lambda is speed of sound, because we're talking about the sound wave here, divided by the frequency. So speed of sound, even if it's not given, speed of sound in standard air pressure and temperature is 341. It will be given 20. Okay, so that's the first thing you have to calculate. And so lambda is this, right? So then what's the length need? You need a length of lambda over 2, so 341 divided by 2 times 20. So length needed is 8.5. So you need a 8.5 meter long length to produce 20 hertz as fundamental frequency. Okay, next is now do the same thing for open close. So one end is open, other end is closed. So that will change the boundary condition, right? That will change, definitely change, because this is fixed or closed. So then if you produce the sound wave, right, sound wave, you can use a speaker, right, a speaker or tuning fork, right, and then produce. So this is the first harmonic. This has to be the first. This should be the position because it's fixed. This should be the antinode. So it has to satisfy this boundary length has to be, so antinode to node is lambda over 4, right? And again, lambda is speed of sound. This is, we are talking about the speed of sound, right, divided by frequency. So speed 341 divided by 20 hertz, and L has to satisfy lambda over 4. So lambda is this 341 by 4 times 20. So that has to be the 4.26. You need much smaller length, almost half the length, if one end is close, to produce the same frequency. Okay, so just try to understand the boundary conditions, right?